Okay, yeah, so today we're going to talk about static dynamic and stagnation pressure. And I have another picture of an airplane on the screen. So basically what's the importance of this is in flow measurement usually. So there's certain devices on airplanes and um, these are on, for example, F1 cars and stuff like that too, that measure the airspeed. So for example, this little device here uses the concept of static dynamic and stagnation pressure to measure the airspeed of the plane. So it's important for the pilots to know basically how fast the airplane is going so that they know that it's going fast enough to maintain lift. And a lot of, there's actually unfortunately been a lot of like airplane related crashes and things like that related to pitot tube issues. So this is basically the way that the pilot knows how fast they're going and when there's issues. So there's all sorts of safety regulations around designing these for real world aircraft. For example, they're heated to prevent like ice buildup. Um, and there's usually a couple of them as well. Sometimes, so this sensor down here is not a pitot tube, it's an angle of attack sensor. So basically the wind blows on that sensor and it tells the pilot how basically the direction of the plane's nose. So sometimes this pitot tube is incorporated in that sensor, but I don't believe in this airplane it is. But yeah, so that's kind of the real world implications of what we're going to focus on today. So from last lecture, we derived Bernoulli's equation. Bernoulli's equation is conservation of energy for a fluid. And we derive this in the normal way that we derive conservation of energy. And that's by integrating F equals ma along a path. In our case, we assumed a steady state flow, so our path is a streamline. We also made several assumptions to make that easier, so I'm going to give a review of the assumptions today. So if those assumptions are satisfied, you get that relationship there between any 2 points um, along a streamline. So along a streamline is one of the assumptions. So in general, between any 2 points that satisfy those assumptions, the energy is going to be conserved. So you have our flow energy there, kinetic energy, and gravitational potential energy. Today, we're still going to be talking about Bernoulli's equation. So later on, like your project is basically is based on extensions of Bernoulli's equation to internal flows. So you'll see over the next couple of weeks, basically how we extend this to more practical cases. You'll see today that this Bernoulli's equation in the original form is quite limited. So learning objectives for today are to distinguish between these 3 types of pressures, to be able to measure flow using Bernoulli's equation. Then the second half of the lecture, we're going to talk more about the assumptions in Bernoulli's equation. So I'm going to list them very clearly, the assumptions I made, and then we're going to do some more interactive activities about where these assumptions might be valid or invalid in common flows. Any questions before we begin? Okay. So I'm going to start off by talking about static, dynamic, and stagnation pressure. So I'll state Bernoulli's equation here. So if we have some sort of streamline, point 1, point 2 along this streamline, Bernoulli's equation tells us the relationship basically between pressure and velocity. So P1 plus 1/2 rho V1 squared plus rho GZ1 equals P2 plus 1/2 rho V2 squared plus rho GZ2. And the Z's are measured from a common datum. So for example, if I choose the orange line as my datum, then my Z's will be like this. So this is all a review of what we did yesterday. So we're going to talk about specific cases now of basically Bernoulli's equation. So let's say okay, so I'm going to say Bernoulli's equation says P plus 1/2 rho V squared plus rho G Z is constant. So total energy is constant. Okay, so the actual terms in this equation are, so the first P, that's what we call the static pressure. So static pressure is the actual thermodynamic pressure of the fluid. So in a thermal class, that's the pressure in your like thermo tables. That's the pressure in ideal gas law. That's the actual pressure. The second term in this is 1/2 rho v squared. And that's called the dynamic pressure. The reason it's called dynamic pressure is it's, well, first of all, it increases when the flow is more dynamic, so it increases with velocity. So what 1/2 rho v squared is in this equation is it's the pressure rise that we get when we bring our fluid to a stop. So if we put something in our fluid and it comes to a stop, the pressure rise from out here to here is going to be that 1/2 rho v squared. So it's the kinetic energy being converted into pressure. So pressure rise when the fluid is brought to a stop. And there's a condition here that you will see the consequences of in fluids too, or maybe the consequences when it's not satisfied. But it's going to be that we isentropically bring it to a stop. So real flows, the energy equation becomes a little bit more complicated. You might remember we don't have any heat transfer in the Bernoulli's equation, so everything's kind of isothermal, no heat transfer, everything's isentropic. You'll see later. So the third term here is just rho gz, and that's what we'll call hydrostatic pressure. And actually the term rho gz, if all you have is this equation here, constant, the term rho gz really isn't that helpful because the choice of z is arbitrary for one side of this equation, right? So it's not that helpful. Because the choice of z is arbitrary. So rho gz becomes important when you have both sides of the equation. So you have a z1 and z2. So it's about the relative change between between z's of our 2 points. And just a reminder, z in this equation is defined positive upward. So if you go back and look at the derivation, which I'll probably jump to throughout this lecture, the z was defined positive upward. Okay. So these are our three. So far, I've given you the definitions of 2 of the objectives here. So static pressure, the actual thermodynamic pressure of the fluid, the dynamic pressure there. We also saw our hydrostatic pressure is not that important, so I'm going to. Okay. So let's talk now about stagnation pressure. So let's say we have some sort of object in our flow. We're going to have some streamlines around this object. We're going to consider a very special streamline here, the red streamline. So the red is it's called the stagnation streamline. Does anyone have a guess of why it's called the stagnation streamline? Because the flow stagnates there. That's right. So stagnation means stopping, basically. So the flow, this is called the stagnation streamline because from 1 to 2, the streamline ends. So the velocity is stopped there. So the velocity at point 2 is 0. The other streamlines go around this point. So let's do Bernoulli's equation here along 1 to 2. So P1 plus 1/2 rho V1 squared is rho G Z1 P2 is 1/2 rho V2 squared, rho G Z2. Okay, so first of all, let's cancel our Z's. So we're going to say these are at the same height. There's not going to be any hydrostatic pressure difference between these 2 points. The other thing we know immediately is that at point 2, the velocity is 0. So we can get rid of that. So this gives us the relation P2, I'm going to do this in orange. P2 is P1 plus 1/2 rho V1 squared. So that's the pressure at point 2. And this is called the stagnation pressure. And it is defined as P, it's usually called P stag, so that we know it's stagnation pressure. And that's P plus 1/2 rho V squared. So here it was like P2 is P1 plus 1/2 rho V1 squared. But stagnation pressure is defined, you can define it at a point. So you would say at point 1, the stagnation pressure is P1 plus 1/2 rho V1 squared. That means at any point in the fluid, if you bring the fluid to a stop there, what is your pressure? So without hydrostatics, without accounting for hydrostatic pressure, the stagnation pressure is actually the total energy in our flow. So that's why it's useful to have a definition for this. Are there any questions on stagnation pressure? Okay. So let's say we had some pressure measurement devices in here. So what the device that I showed on the slide does, it doesn't actually measure the velocity directly. It just measures a couple of different pressures. And from measuring those pressures, you can calculate the velocity in a fairly reliable way. So what the pressures it's going to measure is, if we put a pressure probe at point 2, and we put a pressure probe at point 1, we can calculate the velocity. Say this is the body of our aircraft or our car or something, and we measure these 2 pressures. Oops. Measure those 2 pressures, we can calculate the velocity that our car is moving at. So that's what a pitot tube does. So if we measure these pressures, we'll solve for V1. So that gives us V square root of 2 P stag minus P for, and this equation is appropriately called the pitot tube equation, because it's the basically governing equation for a very important measurement technique. So pitot tube equation. So let's do a quick quiz. So what is P called here? It's one of the terms in this lecture. Static pressure, right? Obviously this one is stagnation. So what we need to do is we need to measure the stagnation pressure and the static pressure. So there's kind of there's a bunch of different ways that this is done in reality. I'll give you kind of 2 common ways here. First way is called a pitot probe. The pitot probe is only going to measure, well, the probe itself only measures P stag. So this is kind of what this device looks like. It's it's nothing more complicated than just a tube that you stick in the flow, and you connect a pressure sensor to the end of this tube. So the flow comes in here. Actually, I'm going to keep the same coloring as we did above. So the flow will go around this tube, and there's a stagnation streamline that comes in here, and it stops here. So the interior of this tube is all stagnated. There's no flow in this tube. So the flow basically can't leave out, let me explain. The flow can't leave out this end. So if you just put a pressure sensor there, the flow can't leave there. And you assume kind of that the pressure is uniform between here and there. Then you basically can measure the pressure, the stagnation point there by measuring the pressure here. So this is usually done with air. So again, we usually neglect hydrostatic head of air. So even though there might be a height difference you can reliably measure the pressure at the red point by measuring the pressure down here, as long as this fluid is all stationary. So that pitot probe idea gives you P stag, and then usually, excuse me, usually like the static pressure, P, because we need that for this equation, P is measured elsewhere. And the reason that P is sometimes measured elsewhere is more of a design consideration. So basically, if we measure P and we measure P stagnation pressure, we can calculate velocity from that. So I would say the more common one is called a pitot-static probe. So a pitot-static probe is really handy because it measures P stag and P, our static pressure. So that's why it's called a pitot-static probe, because you also get the static pressure from it. So here's the design of the basic design of a pitot-static probe. It looks almost identical to our pitot probe. So we have sort of our, by the way, so I'll talk about in a bit the actual design of this device, but I'm greatly exaggerating the scales here. As you saw, this is a very small device. I'll talk about why we want to make it small. So we have our probe. In a pitot-static probe, the stagnation streamline is actually connected through a small pipe in the inside. So that's going to go to pressure sensor. Just to clarify, that would be P stag. Same principle applies there for P stag. So the flow kind of gets backed up in this tube. There's no movement to that flow. The other streamlines and flow will go around like this. Now, the reason that that tube is kept separate is because we also take a static pressure reading like this. So we have a bunch of holes. The design of this varies a lot, but basically the idea is you have all these holes. So what you're going to do, I'm going to draw the streamline here. These holes will actually allow you to measure the static pressure P. So these two chambers are separate, but they're both like for a static fluid. So we need now to measure also the pressure in the green chamber. So that is usually, there's usually like a, something like that. So that green chamber is connected to a pressure sensor over here. And that's going to give us our static pressure measurement. So, um, sorry guys, give me one second. The, the reason that the green measures the static pressure, I'm going to draw maybe kind of a zoomed in view here of what this looks like. So this is of one of the green holes in the front of this device. So you have your streamline that comes over here. So at this point, assuming the flow is still parallel to this hole, at this point the pressure is exerted uniformly in all directions, right? So it exerts the right pressure on our fluid in here, and that's how we measure this. So the design of those holes is very important. And the machining has to be quite precise on those holes, because if you have a little, say some burrs or something like this here, you're not actually measuring, now you're disturbing the flow. So you might slow down the velocity of the flow. So you're not measuring the static pressure anymore. You're getting a mix of dynamic pressure in that measurement. So you don't want, you want this hole to be very like flush with the top of the surface. So this device is really nice because we get a single point measurement and we can determine the velocity. Basically the whole point, I'll write this down because it's important. The whole point of this device is to measure the velocity here. So there is kind of out in the free stream. So maybe, sorry, I don't know what it is today. So maybe let's brainstorm. So what are some important design considerations for this type of sensor, for this type of probe? I talked about one in the design of the static ports, that they shouldn't disturb the flow, right? Anyone have any ideas? Okay, I can start. Oh yeah, okay, we got some ideas. Sweet. Yeah, do you want to go? Sure. Yeah, it can't be too long. Yeah, or else like the pressure might not be a reliable reading, right? Of your, if you read the pressure down here, you might not get a reliable reading up top. So did you have a different point? Same point? Okay. The other thing, so I've greatly exaggerated the scale of this, but you don't want this probe to actually disturb your flow so much. So if this probe kind of backs up your flow, the velocity will actually sort of slow down. So you get kind of a whole stagnation region here. So it won't give you a reliable reading of the pressure out in the free stream, or the velocity out in the free stream. So usually these are like really, really thin devices because you don't want them to actually disrupt your flow. Also, it would just be like an additional source of drag. So I have kind of a surprise. Everyone's going home today with a pitot probe. No, I'm just kidding. Yeah, yep. Sorry, I don't know if I understand your question. Yeah. Um, so you kind of a right idea. So you mean like if it's too small, the pressure will be hard to read, right? So yeah, you obviously can't make it too small. But if it's too big, like your if it's too big, the pressure will actually not be uniform across this plate. So the main issue is that the flow if you zoom in right here, like the main issue is that this isn't a single point, right? So if your flow is coming in like this, and say you design your pitot probe so that it's like something like that, like a flat plate, it's an additional source of one drag, and then also your static probes here won't give you a reliable reading anymore. Because if you don't, normally what's done is, this is very smooth, because if you say have a flat thing here, the flow will come and like it'll mix and you won't get a reliable static pressure reading out there. So I will, no, so no one gets a pitot probe today. So I did bring one though, so you can pass this around. So this is a real pitot-static probe. So you have to look very closely to see the holes basically on the end of this. But how this is used, so see at the end of this, okay, this is the side that measures the actual velocity. So the velocity comes in, the flow comes in like this, and then it's important to get this probe aligned with the flow. So the velocity comes in there and you can see the little static ports as well as the stagnation port there. And these two ends are connected. So there's a very small tube that runs inside this inner diameter all the way out, and that's our stagnation pressure. And then this other tube coming out is our static pressure. So if you have, I showed you this before, it's like a differential pressure sensor. It's actually designed to be connected. You connect one tube to this and one tube to this. Then the difference between those is actually what occurs, is actually what we see in our pitot tube equation is actually about the difference between those. So if we have a differential pressure sensor, we can basically read the difference between those. So please be really careful with this. I'm going to pass it around, but please be very careful with this. It's actually quite a delicate piece of equipment, so you can pass it. You can pass that around. Yeah. Hmm? Yeah, you have to be careful. So for certain devices, like mechanically, you might get, say, it's a very good question. So if your tube is designed with the right diameter, you might actually cause like resonance in your tube and it might bend. So that also has to be able to like withstand the actual aerodynamic forces placed on it. The thing I was just talking about is called vortex-induced vibration. So what happens is, remember we saw like the vortex shedding behind like a very big bluff body. So the vortices are kind of shed like that. So that's a sinusoidal force. And if that can actually cause structural resonance with the thing that's causing the shedding, so that causes a lot of like mechanical vibrations, and that's a big problem. So usually they're quite thin because that makes their natural frequency much more different than a typical vortex shedding frequency would be at that size. So I'm not going to pass this around, but there are other ways to measure flow. Like for example, this is a digital anemometer. So this is like kind of a little fan, but instead of this blowing, you blow on the fan like that. And then this thing is calibrated so that it measures the RPM of the little blades, and then it tells you like a given wind speed. So this is used, I think this is more commonly used in like HVAC and things like that. But there are other ways to measure flow is kind of the story there. So are there any questions about this pitot probe? So make sure when you're looking at that, you see the stagnation port at the very end of it. And also there's very tiny, like the little static, the holes here on the side are the static holes. And those I would say are probably the expensive ones to machine because that has to be a very, very nice finish there. Any questions about pitot tubes? Yep.
The 90-degree bend is just for like clearance for where you put it in, because wouldn't the bottom bend
Yep.
up because you're adding drag? I imagine you add drag because you're going against the
Definitely, yeah.
side.
Yeah, the bend is sort of like, if this thing is long enough, it'll kind of disturb the flow, but you could have just like really long pitot tube. So actually, before I move on, that kind of reminds me. So there's examples of pitot probes on airplanes here. So this is one that's underneath the wing on the right there. So you can see this is much bigger. So maybe you don't carry as much about drag for this plane. So what you talked about there is, could the pitot tube just be a long thing? So that's exactly what happens in like fighter jets. So this thing sticking out the end of the jet is actually a pitot probe. So jets fly at much higher speeds. So Bernoulli's equation, you have to account for basically compressibility there. But this is a pitot probe. So the purpose of this stick, it's not an antenna or anything. It's to measure the velocity. But the reason that you bend that is so you can have like, say you have like a wind tunnel or something, you just stick your probe up in the wind tunnel and you can measure the speed that way. So here's some common examples of them on airplanes. So they also use this in F1. So the pitot tubes are, um, so there's different uses of pitot tubes in F1. So here's a good example of it kind of on the nose of the car. I think they have two simultaneous measurements here. So we're kind of looking on at the pitot tube. So the reason here is okay. So the reason that these stick out, here's a good example. The reason that this sticks out is because this has to be mounted on something, right? So if you mounted the pitot tube, say right there, this is disturbing the flow too much. So you're not getting a good sense of what the speed of the flow is out here because the flow out here starts to feel the presence of this obstruction. So that's why they stick out into the flow. They also use a massive rake of pitot tubes to measure velocity profiles in the car. So they do this during testing. So the airflow is like really complex over a Formula One car, but they're trying to get basically a field measurement of velocity. So there's like a ton of pitot tubes all over this rake. Um, and that allows you to measure a velocity profile rather than sort of a point measurement. Because the one on the front of the car just takes a point measurement of, say, the airspeed there, but this profile allows you to get like a velocity profile. So you can see maybe like the velocity here should be lower or higher, or they also use this to validate a CFD simulation because CFD simulation will give you that velocity profile. Yep, there. Yeah, exactly. Yeah, so if you stick it right at the front, like it hasn't really recovered, you might get like very small like vortex shedding near the front of it. Um, so yeah, that's the reason that the static, it's a very good observation. The static probes, the static holes are usually a little bit further back, so you get nice flow over them. Any other questions? So there's also a really interesting wind speed measuring thing. So this is an observatory. This is a very unique measurement device. So they have a wind vane that uses a pitot probe. The reason is because the wind speed is very, very high, I guess, in this observatory. And like a typical wind vane anemometer, I guess they can't get up to the speeds. Like they said they get like 100 miles per hour. So this is why we don't use like wind vane anemometers on planes. Also, there's a lot of moving parts there. The pitot probe is really robust in that it doesn't actually have any moving parts. All you have to do is measure the pressure coming out of two tubes. So the reason that this wind vane anemometer has this sort of rudder, I don't think this is actually controlled. I think it's passive. The reason is you want it to kind of align your pitot tube with the flow. So if your pitot tube, say your flow is coming in like this, if your pitot tube is misaligned with the flow, you might not get actual stagnation there. So the pressure that you're measuring won't be the stagnation pressure. So that's a potential source of error in pitot tube measurements. Okay. So that's kind of it on pitot tubes. I'm going to list now the assumptions of Bernoulli's equation, then we're going to do some interactive stuff. Any other questions about pitot tubes? You'll see these in the wind tunnels tomorrow. I've asked them to point them out to you. So they have a bunch of pitot tubes because usually you want kind of some reliability in measurement. But pitot tubes are basically what's used the vast majority of time in experimental fluid mechanics to measure velocities. Okay. So let's list now the assumptions of Bernoulli's equation. So the first assumption, and by the way, so I will ask you this on the final. These are really important, okay? The assumptions behind Bernoulli's equation are super important. So know this for the final. First one is steady. Steady state flow. So this means that our streamlines and our path lines and our streak lines are all the same. Second one is it only applies along a streamline. So if two points aren't connected by a streamline, you can't say that energy is conserved between those 2 points. It's like saying like it's a little bit maybe counterintuitive, but it's like saying like the point mass energy conservation that's more from like classical physics. You can't say energy is the same between two different point masses. The streamline actually tells us the motion of our point masses in our fluid. So that's why it's only valid along a streamline. Okay, it's only for incompressible flow in the form that I've shown here. It's for inviscid flow. That means no viscous effects. It assumes no heat transfer. And lastly, it assumes no external work. I'm going to write the equation just to be clear. So we are going to later on, and for your project, you will need to use a modified form of Bernoulli's equation where we relax some of these assumptions, but we also account for them. Bernoulli's equation there on the right-hand side is for all of these assumptions. So we didn't account for any heat transfer. Basically what those do is they're external energy sources, energy inputs into our energy balance. And our equation doesn't account for that. Again, the inviscid flow part was that we kind of removed that term from the Navier-Stokes equations in order to get um, this equation here. Are there any questions about the assumptions here? Okay, we'll finish off with some interactive stuff. So I'm going to try this and see how it goes. So again, the Menti and the code is at the top there. So I'm going to ask you guys here just to rate the restrictiveness of all these assumptions for like, engineering problems. Do you feel like that's a really restrictive assumption? Or do you think like, yeah, like most flows that doesn't really apply, so it's not that restrictive? Again, this is just an opinion thing. I wouldn't say there's a right or wrong answer here. Um, so we have steady state flow is kind of spread. Like, seems like some of you think that's quite restrictive, and some of you don't think it's very restrictive at all. And someone really, really likes this question. Um, yeah, I would say it depends on the flow. Many industries, the flow is pretty much always steady state. Or, for example, you would use Bernoulli's equation to design it for a steady state condition, and then you would use other analyses to account for transient conditions. I'm going to turn that off. um, let's see. We also have incompressible flow only. I would say I would agree that's not that restrictive. Like a lot of engineering flows are incompressible. Inviscid flows, no heat transfer. Yeah, so most times in real flow we have external work and heat transfer. And you might be happy to know that Bernoulli's equation can be extended to when you have external work applied. For example, in your project, you're going to have a pump in your Bernoulli's equation. So that's going to be a source of external work. And you're also going to have in fluids too heat transfer. So you're going to be able to calculate, say, on that fighter jet pitot probe. This was an issue on, say, the Concorde, the jet. The end of that pitot probe, the stagnation, it heats up quite a bit. Okay, hang on. Give me a sec here. I'm going to turn this off. I think I can. Okay, let's go back. So here's a picture of flow over an airfoil. So you just drag a point on your phone and just pick a region of this flow where Bernoulli's equation applies. Does anyone want to like share why they put their point where they did? Or maybe does someone want to share why no one put pick points in like the orange area here? Yep, that's true. That's true. Any other comments or questions about this? I think you guys kind of see it's in that area away from, say, the wake behind the airfoil, right? I'm not sure about point 11 here, so we'll see. Or 11, maybe 11 different people put that. I'm not sure about that. I'll talk about that in 1 second. How about this flow here? Same idea. So I think you guys understand that it's not valid in the unsteady area behind this vehicle. So that would be one of the assumptions that's violated there. I would say the inviscid assumption is also violated behind the vehicle. So that mixing, that turbulence, a lot of that is caused by viscosity. So mixing is a viscous effect. You might notice that where Bernoulli's equation is valid in this flow, there's never any mixing. So when things mix, that usually indicates viscosity. How about this? So this is a sketch of the boundary layer from previous part of the course. Lovely. Okay, so I think most people got this. But I do want to highlight an important point about this one. So A, there is unsteadiness that we can see in the figure, which means that Bernoulli's equation is not valid here. But Bernoulli's equation, even in, say, a steady laminar boundary layer, Bernoulli's equation is not valid as well. Say it's a steady boundary layer. Does anyone know why? Yep, because boundary layers are a viscous effect. So in that airplane one, there's a boundary layer that forms over the airplane. So Bernoulli's equation is not valid in boundary layers because boundary layers are a region of high viscous effects in our flow. So these ones are basically wrong. Everything else is, I would say, right. I'm not sure about those. Maybe there's some flow under the plate that doesn't magically form this very nice drawing of a boundary layer. I'm going to skip this one because this is just the boundary layer thing we did before. So what about this flow? Nice, really good. Yeah, I think you guys are getting this. So again, what I mentioned about mixing and things like that, you'll notice like when we have streamlines. So there are still streamlines over here, by the way. It's not just that it's only applicable along streamlines. There are still streamlines here, but it's that mixing, that viscous effect, that unsteady effect as well, that makes it not applicable over there, assuming this flow doesn't have heat transfer. So this is actually called the potential core of a jet, and that is actually usually a steady part of the flow. So you could apply Bernoulli's equation pretty reliably from, say, here to here. Then once things start mixing and varying too much, that's where Bernoulli's equation isn't valid anymore. So if you take the aerodynamics class, you'll learn what that means about potential flow. It's based on a really similar assumption. Any questions about this one? No? How about this flow? So this this flow is actually good. So these are path lines, right? These aren't, say, back here the flow is unsteady, so these aren't streamlines. Um, the steady part of this flow, assuming say this is steady, that would be a streamline. And Bernoulli's equation, you could apply that along steady streamlines. So you couldn't apply Bernoulli's equation from where that 18 is down to here. One, because this isn't actually a streamline, but also because the unsteadiness. So it doesn't always apply along any streamline. What about this flow? So this is a flow coming out of like a rocket engine. Okay, for this one, I would say it does not apply basically anywhere in this flow. That's because there's a lot of heat transfer going on in this part of the flow. It's also probably extremely fast, so it can't be assumed to be incompressible anymore. So that heat transfer is, I mean, look at the huge amount of energy here. That's not just energy between pressure and velocity. That's energy coming from heat sources and combustion and things like that. So Bernoulli's equation wouldn't be valid in there. I get where you're going with. It looks similar to that potential core of the jet I did previously, but in this case, there's too many other energy sources, so Bernoulli's equation wouldn't be valid. I'm gonna kind of skip this. I think you guys are getting the gist of it. Maybe here is a good one. Yeah, I agree with basically all these. The important thing to notice is, so it's not valid where the fan is. That's because of many issues. It's probably quite unsteady, lots of mixing. The fan is also a source of external work. Once the flow kind of stabilizes past the fan, Bernoulli's equation could be used to connect a point, say here to here, but it couldn't be used to connect a point from here to here because there's an external energy source. So you would have a new total energy on the right-hand side of the fan, and up to the fan, that would be a different, say, total energy. And that's because we've added a lot of energy into the flow with the fan. By the way, there are streamlines connecting, say, the left-hand side of this through the fan to the right-hand side. Streamlines are just instantaneous, valid, wherever, right? But the fan is an external energy source along those streamlines, so that's not valid there. Okay, let's do this one, and then we can end this a little bit early. Okay, so before you put the point down, the question is pick a point in this flow so that point one, the energy balance will hold between point one and your point. I'm kind of seeing the general trend here. So the important thing is that it should be connected by a streamline to point one, assuming this is a steady flow. So are there any questions on that? Yep. Yeah. There's a bunch of reasons. One of them is unsteadiness. Yep. Yeah, and you could approximate the energy input into what happens on the streamline. That's basically how turbo machinery like analysis often works. So you say we're going to do some sort of work input with this fan, and then we can account for that in our energy equation. But Bernoulli's equation, the one that we've looked at so far, doesn't have that term in it. So that's why we say it doesn't apply. Any other questions? Okay, so that's everything for today. I'll see you guys tomorrow.